Let's dive right into this explainer and completely demystify what it actually takes to survive the, frankly, rigorous data science and machine learning interview gauntlet. Let's be real for a second. These interviews, they can be incredibly intimidating. Whether you're gunning for a role as a data analyst or trying to land a spot as a senior AI researcher, the barrier to entry is literally higher than ever. You're going to be sitting across from industry veterans who want to push your knowledge to its absolute breaking point. But hey, don't sweat it. Think of this explainer as your ultimate cheat sheet to not just survive, but absolutely dominate that room.
So start by asking yourself this crucial question. Do you actually know the pass rate for top-tier AI engineering interviews? Well, at a lot of the major tech giants, it's hovering right around 2 to 3%. Yeah, 2 to 3%. Passing isn't just about memorizing some trivia or reciting formulas you crammed the night before. It's really about navigating an escalating gauntlet, starting from basic probability all the way up to visionary research strategy. These interviewers are looking for a profound depth of understanding. They want to see exactly how your brain works when you don't immediately know the answer.
Here's our agenda for today. 1. The statistical foundation. 2. Machine learning mechanics. 3. Model evaluation trade-offs. 4. AI research strategy. And 5. Translating negative results.
Section 1. The statistical foundation. Weeding out the underprepared.
Okay, we're starting at base camp with the absolute statistical essentials. Now, the contrast between dependent and independent events is a totally classic rapid-fire interview topic. And you might be wondering, why do interviewers care so much about this? Well, it's because they want to see if you can accurately calculate joint probabilities while you're under immense pressure. You need to confidently articulate that independent events, like, say, flipping a coin twice, have absolutely zero memory of past results. The coin simply doesn't care what happened before. But with dependent events, like drawing a card from a deck without putting it back, that first outcome mathematically alters the entire probability landscape of the second draw. If you mess up this baseline logic, honestly, the interview might just end right there.
Then there's another really fundamental trap candidates fall into, and that's assuming that just because two variables move together, one inherently causes the other. Correlation simply means two things happen simultaneously. The classic textbook example, ice cream sales and swimming both spike in the summer. Causation, on the other hand, means one directly causes the other, like how studying actually improves your test scores. But okay, here's the real secret to completely acing this question. You absolutely must briefly explain exactly how you'd prove causation in the real world. Toss out that you'd use A/B testing, randomized controlled trials, or counterfactual analysis to separate all that random noise from reality.
Section 2. Machine learning mechanics. Navigating the dense forest of algorithms.
All right, moving into the dense stuff. A staple of any ML interview is explaining gradient descent. This is really where you prove you understand the engine under the hood. And interviewers absolutely love to hear vivid analogies here. So, think of gradient descent as a person trying to blindly climb down a rugged, foggy mountain to reach the absolute lowest possible point. The slope under your feet tells you which way is down, right? And your learning rate is basically the size of the step you take. But here is the critical insight you've got to add if you want to sound like a pro. Mention the danger of getting stuck in a local minimum. That's basically a smaller valley on the side of the mountain that looks like the bottom but isn't the true global minimum. You have to explain how optimizing your learning rate helps you step right out of those traps.
Now, generative adversarial networks, or GANs, represent a massive leap in complexity. The crucial point here is clearly defining the adversarial relationship between two internal networks. You see, you aren't just training one model. You are actually training two competing models locked in this continuous evolutionary loop of trying to outsmart one another. Understanding this architecture is completely non-negotiable right now, especially because GANs are the foundational mechanics behind so much of modern generative AI, synthetic data generation, and yeah, even deepfake technology.
So how do you explain this? The wine cellar analogy is a fantastic way to narratively prove to an interviewer that you intuitively grasp how GANs train each other. Picture this. The generator is a shady dealer producing fake wine. The discriminator is the careful wine seller analyzing the stock. The dynamic is just beautiful. The dealer improves their fakes to bypass detection, while the seller simultaneously improves their detection skills, which ends up pushing both networks to achieve incredible accuracy. When you drop a clear, narrative analogy like this in your interview, you're proving that you don't just memorize textbook definitions. You truly comprehend the underlying mechanics.
Section 3. Model evaluation trade-offs. Balancing competing priorities.
Okay, you absolutely must know how to construct and read a confusion matrix. Let's make sure you have this locked in. The columns typically represent reality, what actually happened. The rows represent your model's prediction, your guess.
And your ultimate goal? Maximizing that diagonal line, matching true positives and true negatives. If you're asked to evaluate a binary classifier and you can't immediately mentally sketch out and explain true positives, false negatives, and true negatives, you simply aren't ready for the role. It is the absolute bedrock foundation for deriving accuracy, precision, sensitivity, and recall.
Now, interviewers will almost certainly ask you to distinguish between false positives and false negatives by providing real-world examples of when one is far more dangerous than the other. Let's think about the actual gravity of this for a second. A false positive, a type I error, could mean diagnosing cancer when there is none, which subjects a completely healthy patient to highly toxic chemotherapy. On the flip side, a false negative, a type 2 error, could mean a bank missing a high-risk indicator and approving a massive loan to someone who's definitely going to default, leading to catastrophic financial loss. Knowing exactly which metric to optimize based on the specific business context is precisely what separates the juniors from the seniors.
Similarly, discussing high bias versus high variance is an absolute masterclass in demonstrating that you can build models that actually generalize to unseen, messy, real-world data. High bias means your model is way too simple and underfits the data. It's missing the big picture entirely. High variance, though, means your model is way too complex and overfits. It's basically just memorizing the noise rather than the actual signal. But you can't just define the problem. You actually have to explain how to find that sweet spot right in the middle. Be ready to bring up actionable techniques like cross-validation to test on unseen data or regularization methods to penalize overly complex models, because that is exactly how you solve the trade-off.
Section 4. AI Research Strategy. Facing the boss level of system architecture.
If you're asked how to convincingly demonstrate a new method's value, step confidently through this layered evaluation strategy to prove your scientific rigor. Don't just point to benchmark improvements. Anyone can do that. Walk them through the steps. Show them you know how to run ablation studies. To put it simply, an ablation study is when you literally remove parts of your model one by one to see what actually drives the performance. You're systematically hunting for the secret sauce, right? Then, you want to discuss using synthetic experiments to verify those mechanics, testing generalization across entirely different domains, and actively searching for failure modes.
I really want to explicitly hammer home these 3 critical evaluation questions. Answering only the first one is the biggest rookie mistake in research interviews. Look, anyone can show that a model works on a standard benchmark. But why does it work? And honestly, more importantly, when does it work and when does it completely fall apart? If you can articulate the exact boundary conditions where your architecture breaks down, you're going to instantly command the room's respect.
Okay, burn this bold number into your memory: 20 tokens per parameter. This represents the famous chinchilla insight for compute optimal model training. But let's unpack what that practically means for you sitting in that chair. If you get asked about scaling laws, this rule of thumb shows that model size and data size need to scale proportionally. If you double the size of your AI model's brain, its parameters, you must also double the amount of data or tokens you feed into it. Otherwise, you're just wildly undertraining a massive network and, quite frankly, wasting millions of dollars in incredibly expensive computing power.
However, what the interviewer is really testing here is your practical maturity. Do you know the exact, messy, real-world scenarios where those beautiful theoretical scaling laws just completely break down? I mean, they aren't perfect oracles. If your main concern is making a model cheap to deploy in production, or say you're fine-tuning an already pre-trained model, or if you simply just lack high-quality training data, well, the standard scaling laws go right out the window. Recognizing these real-world constraints and actually slowing down to explain them proves to them that you have actual production battle scars.
Section 5. Translating negative results. Extracting value from research failures.
Finally, let's look at how elite candidates handle those tough behavioral questions about, say, months of research that simply didn't pan out. Make this personal. When they ask you about a time you failed, please do not give a fake, cliché weakness. Give them one of these analytical frameworks instead. Frame your failures analytically. If the hypothesis was wrong, well, you've saved the community valuable time. If the method needs refinement, you've successfully narrowed the path forward. And if the problem is just incredibly hard, you've mapped the true scope of the challenge. That kind of intellectual resilience, it's incredibly highly prized.
There's an old research adage that goes something like this. A paper with modest improvements but deep understanding is often way more influential than one with big numbers and zero insight. In an interview setting, demonstrating that you deeply understand the limitations, the mechanics, and the underlying trade-offs of your work is infinitely more impressive than just boasting about some high accuracy score that you can't even explain. It shows them you're a true scientist and not just an operator. So now that you possess the ultimate roadmap to survive the gauntlet, the only real question left is, what research problem are you going to choose to solve next? Review these concepts, practice explaining them aloud with the kind of depth we just covered, and walk into that room ready to demonstrate true expertise. By understanding these deeper layers, you've basically already bypassed 90% of the candidate pool. You've totally got this. See you in the next explainer.